Sorry to disappoint. We're going to pick up where we left off last time, doing more of these related rate problems. And in Canvas on our website under Files where your formulas are, there's this document is there. And it's kind of follows what we did in class last time in terms of kind of giving you a template as to how to go about these problems. Some of the things are a little bit out of place. Like I put here to draw the exact moment in time first. We were doing the general picture first. So, I mean, it's all here. It's just kind of mixed up a little bit. So I figured you could use this if you want. I printed a couple of copies so you have a couple on your desk. If you need more, you can go print them off online. On a test, I'm not going to provide you that. So the idea is that you get this kind of in your head at some point, all right? All right, so here we go. We're going to do this problem, and I've got more problems than we have time for, all right? So I'm going to have to pick and choose. This one is a classic problem, okay? Most Cal 1 students will see this problem or something like it. A conical cup is 4 inches tall, 6 inches wide. Water is being poured into the cup at a constant rate of 2 pi cubic inches per second. How fast is the water level rising when the water is 1 inch from the top of the cup? So do you all want to see the animation of this first, or do you want to just try and do it without any visual guidance? No visual guidance? Okay, then if that's the case, let's make this a little smaller. Okay, so I'm going to start putting together some things here. I'm going to still do general here, and then the instant. All right, so what should I draw? A cone, right? A conical cup. Now this cup is going to be a cone. I'm going to draw it, you know, like a cup would be, not pointy side up. So I'm going to draw this cone like this, okay? All right, is there anything on that cone that I can label that's fixed no matter what, never changes in the problem? The width and the height, right? I mean, that cup is fixed. It's 6 inches wide and it's 4 inches tall. Okay, so if that's fixed, what's changing? Yeah, the amount of stuff in it, right? I'm filling it with water, right? Or we're filling it with water. So there's water within this cone. That's the part of it that's changing. So I'm going to draw the water in here. So I'm going to draw like a little water level in there. That blue marker's done. Okay, so I have a water level in here. Now that's changing, yes? As I pour into this, that water level is going to rise. Okay? All right. What next? I really am hoping you guide me through this.
You got 2 pi cubic inches a second, so that's the rate that's flowing in.
Okay, so the 2 pi cubic inches per second is the rate at which the water is going in. So that's something I'm given, right? And what we want here, and eventually we'll get to an equation. Okay, so what should I do then for given? You said the 2 pi cubic inches per second is the rate at which what is changing?
The level of the water.
The level of the water? The volume of the water, right? And we know it's volume because it's 2 pi cubic inches, right? Cubic inches is a measurement of volume. So what do you want me to write here? dV dt, okay? dV dt, that's the change in volume with respect to time. It's 2 pi cubic inches per second, right? That's given to us. All right. What else? We want to know how fast the water level is rising, right? How fast something is rising is a speed. So we want the height, right? How fast the height is changing with respect to time. The problem with this right now, even though we know kind of what we're looking for, if we say dH dt, h needs to be in our picture somewhere. So where's h in our picture? It's the height of the water, right? Not the height of the cup, but the height of the water. So I'm going to label that over here, distance from here to here. That would be the height of our water. Question?
Would that be three inches?
Okay, so that would be 3 inches at the instant that we're talking about. But remember, it's moving, right? And what we want to do is like snap an instant in time. That's going to be this picture. So when we get to this picture, we will fix this height to be 3 inches because it'll be an inch from the top, right? You want me to go ahead and do that now? I can do that now. I can draw the picture of the instant in time. My water level at that instant in time is 1 inch from the top, and that means my height is 3 inches, right? But that's the snapshot picture, right? You can't fix 3 over here. All right, when is it that we want DHDT? Because this has to, we need to know like at the exact moment. So that usually what I've been doing is putting over here like at some particular moment in time. So what would I put there?
At 3 inches.
At what is 3 inches? At
Water level is 3 inches from the top.
which we are calling H, right? At H equals 3, all right? All right, do we have everything we need as far as pictures? General picture, H is changing. Instant in time, H is fixed. Also, this is still 6 and 4, right? That's still 6 and 4 here. Okay, and we are given dVdt, we want dHdt, we want it at the moment that H is 3, and now we need an equation. We need an equation that relates what two variables together? The volume of the water, right? The volume of the water to the height of the water. Very important that you understand, we're talking about the water here, we're not talking about the cone. The cone has a fixed volume, right? And the cone has a fixed height. We're talking about the water within it, which is still in the shape of a cone, but it's not the same as the big cone, right? So what formulas, what equations do we have that somehow relates the volume of a cone to its height?
V equals 1/3 pi r squared h.
V equals 1/3 pi r squared h, and you got that off your formula sheet, right?
Correct.
Okay, so that's our equation. Does it have V in the equation? Yeah, and that's good, right? Does it have H in the equation? Yes, that's good because we want to know what dHdt is. But what's wrong with it? Yes. Yeah, we don't know what R is, right? Like we don't have any information about dr dt. And we know that if we take the derivative of this, we're going to get a dr dt, right? Because R is not constant. The radius changes. As we start pouring water into this, that radius changes. Yes?
I mean, but isn't the radius 3?
The radius of what?
Cone.
Okay, so we're not talking about the cone though. We're talking about the water within the cone. So as you pour water in, the water, this cone, this blue cone is changing, right? So its radius changes. Yes?
1.5.
It's going to eventually get to have a radius of 3 if we fill it up. But when we're lower, it's got a smaller radius, and when we're really low, it's got a really tiny radius. So that radius is changing as we're pouring the water in, yes? So R is a problem, isn't it? R is a problem. So we have to figure out a way to resolve that issue. Yes?
So would it be wrong in moving this equation around to get from R and then subbing that in for R?
To move this equation around,
So you solve for R
solve this for R,
and then plug that into there? Would that be wrong?
and plug that into what?
As R. And like, so you got this equation and then like on the next line you solve for R and it should be like V over 3 pi.
Got you,
H.
got you. And then plug it back in there?
Yeah, would
If
that
you
work?
do
Would
that,
cancel it out?
yeah, what'll happen is you'll get just like a statement at the end that says like 1 equals 1.
Yeah.
So it won't tell you anything. Okay, ready? We got to move through these. This is one of those problems where I'm just going to show you, and now you kind of know. All right. So what we're going to do here is we need to somehow eliminate R from our equation. All right. We need to eliminate it, somehow replace it with something that has H's and V's. That's the most that we can do is try and make this R become something with H's and V's. Everyone understand the issue? Okay, so what we're going to imagine doing now is we're going to imagine taking our imaginary sword and cutting through our cone right down the center. okay, and peeling it open, imagining the water doesn't spill out, okay, and looking at a cross section of this picture. If we look at a cross section of this cone, it'll look like a triangle, right? And within that triangle, we will have the water level. And remember, this is arbitrary. We are in this picture, not this picture. We only look at this picture after we differentiate. So we're looking at this. So that water level in here is somewhere, right? Now, come straight down, drop a perpendicular straight down the center. And what you've created, if you can look at both sides or just one side. I'm going to look at just one side. I've got similar triangles again. And this is a problem like the light pole problem, kind of. So let's take a look at these triangles. I have the black triangle, right? And then I have the blue triangle inside of it, right? This blue triangle right here. I'm going to draw that separately. Are these similar triangles? They're similar because they have congruent angles. Their angles correspond, right? We both have 90s here. They both share this angle, right? That angle has to be the same here and here. And since those are the same and the 90s are the same, that means this other angle has to be the same. So we have similar. Yes? Okay, now do we know anything about the black triangle in terms of the sides?
The top is 3 inches.
This from here to here is 3, right? Because that's the radius of the cone. Half of the 6, and then from here to here we know is 4, and then here, what's the height of the water? H. We don't know what that is, right? It's just some arbitrary value H. And then what is the radius of our water? We don't know, but we'll call it R, right? And so what we will be able to do now is use similar triangles to somehow come up with a relationship between R and H. And once we establish that relationship, we can solve it for R in terms of H and then plug it back in here, all right? But everything is based upon this geometry right here. Okay, so now let's set up the similar triangle. I'm kind of going to run out of room here, so I'm just going to squeeze it in right here, but just understand it's not part of this. From last class, what did we say? Like once we have similar triangles, what can you do with this? You can create ratios, right? However you want. So I'm going to let you create it. What ratio do you want me to create? R over 3 equals H over 4. Okay, I'm going to write that down. R over 3 equals H over 4. That's one ratio you could set up and work with, and that's probably going to be the easiest one for us to work with. What, just for the sake of talking through it, what's another ratio I could set up?
Could you do 3/4 is equal to?
I could go 3 over 4 is equal to R over H. Okay, I could go 3 over 4 is equal to R over H. Any others? There's a couple, right?
Yeah.
You could go 4 over H equals 3 over R. You could go H over R equals 4 over 3. What you could not do is 4 over R equals H over 3. That you're not allowed to do. It has to be corresponding sides ratioed, or you have to be working on the same triangle. So H over R, 4 over 3. Understand? Okay, so these both will work out no matter how you do it. Like if we just algebraically manipulate either one of these, we're going to get the same result. So what are we trying to replace? We're trying to get rid of the R, aren't we? So let's just solve this one for R, which will be real easy. We just multiply both sides by 3. So the radius is 3/4 the height. That's what that's saying. For this particular cone, whatever your height is, your radius will always be 3/4 of that height. And that only works within this cone. We change the cone, this changes, right? Okay, so now we come back to our equation that we want to differentiate at some point, and we replace the R, right, with 3/4 H. So 3/4 H, I still have to square it and then multiply times H. Right, so this is R squared. So let's now square this. When you square this, you have to square the fraction and the H, right? So the fraction squared is 9 over 16, and then we're going to move it out front with this right here, right? So the 9 and the 3 reduce. Yeah, we should get 3 over 16 pi Everyone understand that? 9 over 16 times a third, things reduce. We still have the pi. We still have what? H squared times h, which is h cubed. So this, I'm going to box it. This is our new equation. So I'm going to ask a question and see, just listen carefully and see, let's see how you do with this. Have we just come up with a new formula that will give you the volume of any cone if you just tell me what the height of the cone is? No. Why not? What does this do?
We use proportionality, and so
it's only for this cone, okay? That volume height relationship is only for this cone, all right? Okay, so now we have an equation that has just v and h in it, so we differentiate now with respect to little t. So when we take the derivative of the left side, okay, this is our differentiation time, so the derivative of that side is just dv dt. And then remember, all of this is a constant, right? All of that's a constant, so it's just going to come for the ride. 3/16 pi times, now the derivative of h cubed, 3h squared times dh dt. That's our chain rule, right? The all-important chain rule. And now we just take a look at this. dv dt, we are given 2 pi. This is all a constant. We need to know what h is, but now we can snap the picture, right? Now we can freeze everything in time. Do we know the height of the water at the moment in time? 3, right? dh dt is what we're trying to solve for. So let's just finish it out. We've come this far. So what we have now, filling things in, would be dv dt, which is 2 pi, equals 3/16 pi times 3 squared times dh dt, right? So just right off the bat, I'm going to divide both sides by pi, and those are gone. And then, let's see, what am I going to get here? 9, and then times 3 is 27 over 16, right? 27 over 16. Why are y'all looking at me like, everyone's looking at me weird? Y'all all right?
Wait, the 3 times 3 becomes 9 over 16.
Yeah.
What, the what?
9,
Oh, I forgot this 3.
yeah.
That's what I see. I could tell y'all were looking weird. Okay, there's a 3 in here. Yeah, my fault. Yeah, so this is going to be like 9 times 3, so it's 81 over 16. So 2 times 81 over 16 times dh dt. And then we can multiply by the reciprocal, right, on both sides. So multiply the top by 16, divide by 81. So what, 32 over 81 is dh dt. And let's go ahead and get that as a decimal, and then we'll talk about the units, like what's the unit answer here. Okay, there it is. 32 divided by 81, right? Approximately 0.395. What? So we look at the height. Height was measured in inches in this problem. So it's going to be inches over time. Time in this problem was measured in seconds. So inches per second. So if you have a cone 6 inches wide, 4 inches tall, you start pouring water into it at 2 pi cubic feet or cubic inches per second, then you should expect that at the instant the water is 1 inch from the top, that it will be coming up, the water level will be rising at almost half an inch a second at that point. All right, now let's take a look at the animation.
Yes, sir.
Yes.
On the test, I don't know if it's a big deal or not. Would you rather us put it at like
A decimal or exact answer?
yeah?
I don't care. Either way.
Thank you.
Yep. So the idea here is that because this is a cone, As you start pouring liquid into it, initially, because it's small at the bottom, the level's going to start rising fast. But because it spreads out, as long as we're pouring it at a constant rate, it should slow down in terms of the height, like how fast it's coming up. So here's the animation, and you can see I have the computer automatically pouring in at the constant rate, and you can see it's slowed down, hasn't it? And this is the idea over here. This is the construction of the similar triangles. We have the water within the triangles here. So this one changes, the blue one changes, but it's always fixed in that similar triangle ratio. All right, let's move on. Oh, the runner and the track problem. I got in trouble last semester, and one of my students came to my office after we did this problem, and I don't know if I want to say complained, but I'll explain to you. Let's read through the problem first. So a runner sprints around a circular track which has a radius of 50 meters. She runs at a constant rate of 7 meters per second. Her friend is standing at a point 100 meters from the center of the track. How fast is the distance between the two changing when the two are exactly 120 meters apart? So I think I got this problem out of the book. And so last semester I was talking to my class about it. I was like, this is kind of a weird problem. Like what friend is going to be standing 100 meters away from the center of the track watching the other person run around a track? It just seemed kind of stalkerish. And then once I said that just, you know, I don't know, it made some people uncomfortable, I guess. I think y'all can handle that though, right? You can handle that? So I'll leave the problem the way it is, all right? We've got a friend watching somebody, watching their friend run around a track. So the way I like to think about this is what's being asked is this. As the person runs around the track, okay, so I'm watching this person run around the track. If there was like a rope attached to me and the person running around the track, then the rope is going to be going out as they run away from me, right? And then as they come back towards me, it's going to come in, and then it's going to go back out, and then come back in. Does that make sense? The rope would be coming out and going back in as they go around. It's saying at a specific instant in time, how fast is that rope coming out of my hand? How fast is the distance between me and that person changing? Does that make sense? So let's draw a picture, all right? So what should I start with? Circle. Okay, let's start with a circle. And I'm not going to do general, instant, and all that because I need to get my head around the problem first before I get too locked into anything. So here comes a circle. Wow, that's as good as it's going to get right now. That's actually not that bad, yeah. Someone told me a long time ago, if you use the hand you don't normally write with and you go backwards on a chalkboard like that, or on a board, that you can get a really good circle. Apparently that doesn't work. Okay, here's our circle, right? And anything about that circle that's never changing? The radius is 50 meters. I mean, we don't get to choose that, right? So I'm just going to put like a dotted line out here. I'm going to say that's 50 meters. All right. We have somebody running around this track, right? So I'm going to put them somewhere. Where? Anywhere. Okay, anywhere. But let's put them somewhere interesting, like here? I don't know. Here? This okay? Is that all right with you? There's my runner. Okay, where's the stalker? I mean, the observer. Where's the observer? 100 meters from the center of the track, which could be anywhere outside the track, 100 meters away from the center. Doesn't tell us where, so we get to pick, right? Now, if this is 50 meters, wouldn't it make sense just go out another 50 meters, just put it here so everything looks level? I mean, like I could put it up here, or down here, or straight down, or over, but I'm just going to go straight out to the right. So if I go like this, all the way to here, that's my observer. And I know that that distance from here to here is 100 meters. Right? Those things don't change. What else can I put in this general picture?
7 meters per second.
7 meters per second is the speed of the runner, isn't it? So you have to be careful here because how do you put 7 meters per second here? I mean, is 7 meters per second, like where is that on here? It's the speed of the runner, right? But the runner's running in a circle, not a straight line. So I can't, like if this person were running in a straight line, then I could call that side, like if the runner were running like that, I could call this x, and then say, oh, x is changing by a rate of like 7 meters per second. So dx dt would be 7. Does that make sense? We did that on the light pole problem. But see, it's not linear motion, it's circular motion. So I will label it. I'm going to go 7 meters per second here, but I want us to understand that that's the runner's speed around. Now, clockwise and counterclockwise doesn't matter, because if she's running this way, then she's running away from the observer, right? But on the other side, she'd be running towards the observer. So if you're looking at this, the rope between them, if they were connected, the rope between them would be coming out of this person's hand, right? But if she were down here, like reflected down, the rope would be going in, but it would be the same rate either way. All right, anything else we want to label? This is my general picture. Between them, is that what I heard?
Yeah.
What were you going to say, Dib?
Oh, yeah.
Yeah, let's label the distance between them. That would be the straight line distance between them. Now, is that changing? Yes, that's always changing, isn't it? So let's call it something. Let's assign a variable to it. So it's your choice. I would the one variable I advise you to stay away from is using the variable little d. And the reason is because if you need to take derivative of that, it's going to look like this, dd dt. And to me, that's just always looked odd, but there's nothing wrong with it. I'm like, you could do it. I always stay away from little d. I'll use a capital D sometimes, or I'll just use some other letter like Z or H or something. I also don't want to use X or Y, just personally, because I like to use X when I'm horizontal and Y when I'm vertical. But again, you call it what you want, all right? So what do you want to call it? D? Little d? Yeah, thanks. Thanks. Yeah, appreciate that. I'm going to go with Z. I'm just going to call it Z. When I was back in Cal 1, I think I wrote, like my 2's look like that and my Z's look like that when I was like in Cal 1. And so if you're still doing your Z's like this and you're an engineering person or STEM that you're going to go on and do more of this, I would start striking your Z's. That's just a good habit to get into. Also, your T's, if you draw your T's like that, then I would advise that you curl your T's on the bottom so you don't think that they're pluses. Or if someone else is reading your work, they don't think they're pluses. There's little things like that that you can kind of pick up. All right, we keep going. Anything else on this picture? Maybe the instant in time picture would be worth drawing now. So at the instant in time, same picture, runner there somewhere, right? We know that this distance from here to here is 50. We know distance from here to here is 100. And what is the distance between them? 120. Right? That's the instant. So this is our general. I'm just going to put G here for general. This is my instant. Agreed? What else? Yes?
Are they in feet or meters?
They're in meters. Okay, you want me to label them? I will. They're meters. Meters, meters, meters. Speed, what about speed? The 7 meters per second?
Yeah.
That's what? What do you want me to do with that?
I was gonna say, should you label it on the thing?
Label it where? You want to label that here? Okay. Now, on this picture, we're taking the snap. Sorry, on this image diagram, this is a snapshot, right? So in reality, that person's like not moving, right? It's like, right? And so everything's frozen. Here, everything's moving. This moves, Z changes, right? But here, it's like freeze everything. That person is not moving, so to speak. Yes?
Would we be able to, I don't know if it's necessary or not, but like if we'd be able to like mark the speed of like the thing going back and forth, like between the people, the rope?
The speed at which this is changing?
Yeah.
Yeah, that's what we're trying to find. That's what we want to know. We want to know how fast this is moving at exactly that moment. Right?
Okay.
What? Circumference of the circle? That's going to be fixed, right? The circumference? I can get that. Why would I want that?
That's how you're gonna calculate it.
So you're ahead of, yes, you're there. But I want everyone to see why we need the circumference and why we need to do that. So when you're going through these problems, I said you want to draw your pictures, you want to write down what you're given and what you want, right? And that you don't have to go in any particular order, just start getting all the information here. So I think we've drawn pretty decent pictures. We still haven't written down what we're given and what we want yet. Okay? That's what I was hoping someone would say. So what are we given and what do we want? And you don't have to go in any order here.
We want DZ.
We want dz dt. Okay, that's what we want, dz dt. We want to know how fast the distance is changing between them, right? When exactly at the moment that z is 120. Does everyone agree with that? We want to know how fast z is changing with respect to time, how fast that rope's coming out of our hand at exactly the moment that the runner and the observer are 120 meters apart. Okay? What are we given? We're only given one speed in this entire thing, one rate, one derivative, so to speak, and that is the speed of the runner. So we want to call it something, right? d something, or d something dt. The problem is we can't assign a variable to this again because this is not a straight line. All right, so here's where, you know, in the last problem we had to chop it in half and open it up and kind of see. Here's what we're going to do. I'm starting to think ahead to the equation. Eventually I'm going to somehow need to come up with an equation, right? That relates z to something. Yes? Right now, that's all I know about z, and this almost looks like it wants to be a triangle, but it's not a right triangle, because as this person runs around, it's not a right triangle. But what I could do is this. If I connected from the runner down to the center of this circle, and then from that over to here, that triangle has two of its three sides always the same, fixed, right? This is always 50, and this is always 100. So I can't like call these variables, right? The only other thing in here that's of any use to us, and that is somehow related to the speed of the runner, is how fast that angle is changing. This we can call theta. And that angle, do you agree, changes as the runner goes? And shouldn't the speed at which that angle changes be constant? If the runner's running at the same speed the whole time, right, then that angle is changing at the same speed all the time. We have to figure out, though, how fast it's changing. And that is the part that's given to us. So this is where we have to make that leap from what we have is circular speed, or right, it's linear speed around a circle, and we need to somehow convert that to angular speed. That's what we need to do. And this is a pre-cal thing, but we can do it, I think, without going too far off the cliff. We're given d theta dt. We are given that, but we just don't. It's not 7 meters per second. All right, we've got to figure this out. Do you all understand that? So I'm like, okay, I want dz dt. What the hell am I working with? I can draw that triangle, and then I think there's a way to relate that angle to that side. There's got to be some pre-cal formula that somehow relates this side to this angle. If you know two sides, I don't know. There's got to be there. We'll cross that bridge when we get to it. Let's try and get what d theta dt is.
Going from linear to angle.
So it's linear to angle, isn't it? V equals WR.
Yeah, so there's all these formulas, right, from pre-cal that you could have memorized. But I look at it a different way. It's just, to me, this just makes more sense, and it doesn't require any formulas out of my head, really, like that many of them. If you just take this circular track, right, and just snip it and lay it out flat, right? So imagine you just take that and lay that entire circle out flat. Then how long is that? How long is that distance there? It's the circumference of the circle, right? Okay, so it's like instead of looking at this person as running around a track, just cut the track open, lay it flat, and it's like they're running a straight track. And that distance is the circumference of that circle, which is 2 pi times the radius of the circle, which is 50 meters, which is 100 pi meters. Do you all agree that's how long the distance is around the track? Okay. How long does it take for them to cover that distance? So how much time, I'm going to put here t, how much time does it take for them to actually go around this track one time?
1.187.
So where are you getting that from?
I divide 7 meters per second
Into,
to the 100.
yeah, so this is the distance, right? This is how many meters they have to run, and they're running 7 meters every second. So if I take that number and divide it by that number, meters, and I divide that by 7 meters per second, then I'm going to get, what does it come out to be?
44.879, so 41.88.
Yeah, so you can get a decimal here, right? What I'm going to do is I'm just going to leave it as 100 pi over 7. I'm just going to leave it. I'm not even going to go to a decimal. 100 pi over 7 is how many seconds it takes to run around this track. Do you all agree? Okay. Now, if it takes that many seconds to run around the track one time, then that means it goes through the entire angle 2 pi in that amount of time. So when we're looking for d theta dt, it's going to be the angle we go through, which is 2 pi, divided by, that's 1 revolution around the track, divided by the amount of time it took us to do that, which is 100 pi over 7. So back in pre-cal, you probably saw this formula, omega equals theta over t. And yes, does that look right? So theta is basically the angle you travel through. So we traveled through the angle of 2 pi, and how much time did it take us to do that? It took us this much time. So that cleans up. Now you see why I didn't do decimals? The pi's cancel on this one. Remember, this is the same as 2 pi over 1 times 7 over 100 pi, right? So you just get 7 over 50. So at the end of the day, our d theta dt is 7 over 50. Now, very important. What are my units here? Radians per second. Radians per second. It's not degrees. It's not degrees because we said 2 pi, right? 2 pi was the angle. We didn't say 360. In fact, this formula doesn't work in degrees. The formula changes, and so anytime we use those formulas in pre-cal, we always had to be in radians. All right, that's it. We know that this changes at 7 divided by 50, whatever that is, radians every second. That's how fast that angle is changing. And we're trying to figure out how fast z changes. Yes?
It could be 2 pi again, or d theta.
Remember I said, do you remember I said we wanted to figure out like what was the distance around the track one time, right? That was our distance. So now we ask, what's the angle that it takes to go around the track one time? And that's 2 pi, right? 0, pi, 2 pi is all the way around. All right, we ready? What's next? You need an equation. You need some equation that relates this angle to that side.
That angle, that's, wouldn't that be like a sine, negative b, or triangle angles from trigonometry?
Which one?
Either law
It's either law of cosines or law of sines. It's going to be one of the two. Now, I don't expect that you were like, oh yeah, sure, law of cosines, okay? But you need to understand that if you have a triangle, if you know an angle, and you know the two sides, you have two sides and you have the angle between them, there's a formula for it, and then the side opposite, right? So law of cosines, if you look on your formula sheet, or back to pre-cal, it says if you have an arbitrary triangle, I know this is off camera, tough deal with it. Okay, so if we call this angle A, angle B, and angle C, and this side little a across from angle A, and this side little c, and this side little b, then let's do law of sines. Law of sines says sine A over little a equals sine B over little b equals sine C over little c. Okay, but then law of cosines says a squared equals b squared plus c squared minus 2bc cosine of a. But you could also do this b squared equals a squared plus c squared minus 2ac cosine of b. And then there's a third one. But they're all the same formula, okay? They're all the same. They're all the same in terms of if you want to know the angle A, right? Here's little a. All you need to know is, little b, little c, little a, and you can find that angle. Yeah, no, this is pre-cal, so I don't want to get too deep into this, all right? This should allow us to set up an equation. We have an angle, we have the side opposite of it. And so by using law of cosines, my equation is going to look like this. I'm completely out of room because my pictures were too big. I'm going to say, let's just treat this is like our little a, and this is like our angle A in the formula, in this first one. And then B and C are the other two sides, 50 and 100. So it should be what? Z squared equals 50 squared plus 100 squared, 2 times 50 times 100, cosine of theta. There we go. Is that an equation that relates theta and z together? Absolutely. Absolutely. So we could clean that up, couldn't we? We could clean it up. But I'm just going to take the derivative right now. Just going to do it. Okay, so here comes the derivative with respect to time. What is the derivative of z squared? 2z times dz dt equals, what's the derivative of 50 squared?
0.
Plus derivative of 100 squared.
0.
Okay, minus, now this is all a constant, right? So that's a constant attached to cosine, so it's going to stay. So what is that? Minus, is that 10,000? 10,000, right? That's just this constant. And then now I have to take derivative of cosine of theta, which is negative sine of theta, right? So I'm going to make this a plus now because the negative from there. Negative sine theta, drum roll,
Times d theta dt.
times d theta dt. Okay, chain rule. Derivative cosine of something is negative sine of that, and then times derivative of the argument, all right, which is d theta dt. So let's start looking at this differentiated equation. All right, we know z, right? At the moment in time, we can snap our picture. Z is 120. dz dt is what we're looking for, right? That's what we want. 10,000 is just 10,000. Sine of theta. Uh-oh. Uh-oh. Okay, d theta dt. We have it, right? The only thing I don't know in this is what is sine of theta. Right? We don't have that given to us. So we have to figure out what that is. But now we can snap our picture, right? And if we can snap our picture, then here's our picture, right? Here's our angle. Right? Theta. And that theta is fixed. We just need to figure out what it is. So we can just go back to the formula we just used right up here, right? This formula right up here, not the differentiated one, this one. I've got to erase stuff, sorry. So if I take my original formula, z squared, but fix it in time, what's z? 120. So I'm trying to find theta right now. 120 squared equals 50 squared plus 100 squared minus 2 times 50 times 100 times cosine of theta, right? These are all numbers except for cosine theta. So we need our calculator here. I think we do. I'm going to do 120 squared. I'm going to subtract 50 squared, right? And then subtract 100 squared. Y'all follow me or no? And then I'm going to divide both sides by 10,000, or negative 10,000. I'm getting, at the end of all this, that negative 0.19 equals cosine theta. Is anyone else getting that? Yes? Now what? We're trying to solve for theta, right? So how can I get theta by itself on this equation? Inverse cosine both sides. Inverse cosine. So I'm going to do arc cosine on the left and arc cosine on the right, but when you do arc cosine on the right, it kills off the cosine. So inverse cosine on both sides. And then for this, I'm going to use my calculator, and I'm going to just make sure I understand what mode I'm in. I'm going to be in radian mode, so whatever the answer is here is going to be in radians. Am I in radian mode? No, I'm not in radian mode. So arc cosine of negative 0.19, I get something like 1.76. All right. So if I know what theta is in radians, then I should be able to go back here now and figure out what sine theta is. Okay, here we go. Time for the final answer. Leave that there. All right, so here's our final answer. We're trying to solve for dz dt. We have 2 times z at the moment in time is 120 times dz dt equals 10,000 sine of that angle, 1.76, times d theta dt, which we said was what? 7 over 50, right? That's this. So I'm going to get on my calculator and I'm going to type all this in right here. And then when I'm done, I'm going to divide both sides by 240.
Make sure we're treating it.
Yes. So initially, here's what I got. Before I divided by 240, I got 1375.02 about. Anyone else get that over here?
Yep.
Okay, now divide that by 240. dz dt is approximately 5.73. 5.73. Z is the distance between them, right? And so distance here was measured in meters. So this is going to be meters. And then time was measured in seconds, so meters per second. So as this observer very, very creepily, if that's a word, creepily watches their friend running around the track, at the moment the distance between them is 120 meters, the theoretical rope connecting the two is coming out of that person's hand at a rate of 5.73 meters per second. That's rope burn, right? That's rope burn. And that will change. Like as that runner goes around the track, that is going to be varying. Depends on where they are on the track. One way you could kind of perceive that is, think about this. Here's our observer, right? At the instant the runner is right here, what's happening? Think about it when the runner's right here, running around the track, what is the distance between them? What's happening to it? What is your idea? If I had a rope attached to this person, right, and they're running around, as they go around, this is rope burn, right? The rope's coming out of my hand. But when they get right there, at that instant in time, what's happening to the rope? What do you think? It should be zero, right? Like, it should not be pulling out of my hand at that instant. Does our formula account for that? Look at our formula. This is the formula, right? What's the angle? What's the angle when the runner's over here? The angle of our triangle? Pi, right? And what is sine of pi? 0. And that kills this whole side off, right? And then you get, this doesn't matter because it's going to still be 240, or not 240, it's actually going to be 100 plus 50, but it won't matter. Whatever number this is 0, you divide it, dz dt is 0. That's pretty awesome, right? To think that that formula works, like it's just going to work everywhere. What about, with that same idea, when would dz dt be the biggest it could ever be? When? You think where? Right here? Right here? You think, okay, so think about this right here. The rope between them at that instant, you think that the rope's coming out really fast there? Wouldn't these two be the equivalent? Right? Because like if this person's here at this instant, you can look at a tangent line, and if that rope's connected, it's like that tangent line is telling you how fast the rope's moving, I guess, and it's not moving this way, it's straight up and down. And same thing with here, right? Straight up and down. I'm just saying, look at this expression right here. When would this be the biggest it could ever be? When this is the biggest it can be, right? Because whatever this is, no matter what, this side's being divided by this, right? Should be when this is as big as it can be, which would be pi over 2, which would mean the runner's here or here. So when the runner's there, that's when the rope should be coming out of your hand the fastest. Anyway, okay, we can get into that more, but let's do another example. We're already halfway through class. We've done 2 problems. So there's a problem with a ladder sliding down a wall. I'm not going to do that one. So before class, I put together this little animation. And since I took the time to put it together, we're going to work it. So the 2 problems we've done today. The first problem we did with the cone required that we know some geometry with cones, right? And then cut it in half and know similar triangles. This problem we just did required some law of cosines. That kind of came out of nowhere, right? But there it is. All right, this one Like I said, I made the problem up. At 1 o'clock p.m., a man starts walking due north at a constant speed of 4 feet per second. 10 seconds later, a woman who is standing 120 feet east of where the man started begins to walk west at a constant speed of 5 feet per second. At 1:20, that's 20 seconds later, how fast is the distance between the two changing? So this is very similar in the sense that you've got people, you're interested in how fast the distance between two things are changing. This time we don't have an observer watching a person. We have two people that are like moving relative to one another. Right, so they're both in motion. So here's my, yeah, he's following. It's even worse, following them home. Okay, see, I'm gonna get in trouble. Don't get me in trouble. So here's my animation. And I even have the time and everything. This is like 1 second, 2 seconds. So this is when he's walking north, right? She's standing here 120 feet to the right. And then at 10 seconds, she starts walking, all right? And we want to know at exactly, what, 120? Which would be almost there, right? At that instant right there, how fast is the distance between them changing? So we're interested in that distance between them, right? Start it over. So right now, he's just moving. She hasn't started her motion yet. And now we start the motion, so we can start talking about the distance between them, right? This blue line, it's changing. The length of that is changing. Depends on where they are, right? And so we want to know at that instant, 20 seconds, how fast was that blue line either shrinking or growing? Understand? Okay, so I gave you the picture already, but how are we going to do this? So this problem's a little weird because you have something that starts in motion before the other one starts in motion. So I like to do these problems as follows. First, I'm just going to start drawing like what's happening. At 1 o'clock, right? At 1 o'clock, what do we have? We've got this guy standing here, right? This is our man, I guess. And then this is our woman. She's 120 meters to the right of him, or feet, sorry, 120 feet over here. And she's due east, right? She's east of him? Okay. I'm sorry. I'm going to get in trouble. I'm going to get in trouble. Shut up. Stop thinking. I need to just stop thinking. Okay, now, what's my next picture? What's the next kind of important point in time? 10 seconds later, that's when she starts walking, right? So 10 seconds later, at 1 o'clock with 10 seconds, right? She starts her motion, right? So at that instant, she's still where she started, right? She's still there. But where is he? He's gone 40 feet that way because he's walking at 4 feet per second and 10 seconds has passed. So 40 feet, right? So he's now up here, and this is not drawn to scale, okay? This is just, that's 40, right? And this right here is still 120. I'm just trying to get a feel for what's happening. That's all I'm trying to do. The next important point in time would be, you got a question or no?
We're just trying to make sure we're at the 40 came from the 4 feet per second.
He's walking at 4 feet per second, and we're 10 seconds later, because it said 10 seconds later the woman starts walking. Okay, so now 10 seconds after that, right, at 10:20, not 10:20, at what? 10:20, where am I getting that from? At 1 o'clock with 20 seconds gone by, we are now, where is he? He's now 80 feet from where he started, because he's been walking for 20 seconds now. And she's now where? Where is she? She's been walking for how long? She's been walking for 10 seconds, and she walks at 5 feet per second. She's walked 50